For electrolysis, we have galvanic cells in the reverse. So when you calculate a voltage for a chemical reaction and you come across a negative voltage, that means that that process won't happen by itself, but if you put energy in, it will. So the question says, what voltage is necessary to force this reaction to happen? With electrolysis, we have the bonus of not getting to choose what they give us. So we saw this a little bit before, but we are given the half reaction, 2 iodines turning into I2 plus 2 electrons. You have to look up you've got the 2 electrons, and that is a negative 0.54 volts. Okay. We also have, and this is just the way they gave it to us, copper 2 plus 2 electrons turning into solid copper, and that comes out to a positive 0.34 volts. Now, if this was a galvanic cell, we wouldn't choose to do it this way. We would reverse them. Those 2 electrons will cancel out to give us our balanced equation, but our voltage comes out to be a negative 0.20 volts. So the question, how much voltage is necessary to force this to happen? As long as we overcome that 0.2 volts, we can make a positive reaction happen. So that reaction could go forward if we put in 0.2 volts of energy. Anode and cathode is going to be the same thing. The iodine is happening at the anode, and the copper is happening at the cathode, because that's still which one's oxidized, which one's reduced. And because we need a metal electrode, this says assuming the iodine oxidation takes place at the platinum electrode, what is the direction of the electron flow? So we can see that the electrons come off of the iodine and onto the copper. So the electron flow would be from the platinum electrode, which is in the iodine half cell. The electrons would flow to the copper cell, and they would be added into the copper solution to make copper solid. So from anode to cathode still, but we would say platinum to copper. For this reaction with water, we get the question, water is able to pass through it. For the decomposition of water, which process occurs at the anode and cathode when we put a current through water? Now, it's tempting here again to make a galvanic cell, reverse the top reaction, and add them together to get a positive voltage, but that's not how it works. Something else that happens with electrolysis is when you put an electric current through a solution, your balanced equation needs to match the chemicals that are in the solution. For example, if we're putting a current through water, water better be our reactant. So we look for our balanced equation and we can see that water is here and here. I don't have oxygen or hydrogen available. I have water. We're putting a current through water. That tells me that I have to leave this reaction alone and I have to reverse this reaction because I need my reactants to be reactants. So once I reverse that, I will get 2 H2Os turning into oxygen plus 4 H pluses plus 4 electrons. Now we do need to multiply this one times 2 in order to get the electrons to have 4 electrons at the anode and the cathode. So we would get those 4, oh, I missed that there. We would get 4 H2Os plus 4 electrons make 2 H2s and 4 OH minuses. That tells us which ones happen at the cathode and the anode. The reduction happens at the cathode, and the oxidation that we reversed happens at the anode. Once we reverse and simplify this reaction, so we add all this up, and we multiply the top one times 2. We've got 6 H2Os plus, well, that'd be the electrons. That's going to go away. Turns into 2 H2s plus O2 plus 4 H's plus 4 OH's. And you'll kind of see here what happens is these combine to make H2Os, 4 H2Os, and then I can simplify my 4 H2Os and my 6 H2Os to make 2 H2Os. So we're left with a very familiar reaction, 2 H2Os with 2 H2s and an O2. That's how we arrive at that equation, but you'll notice that there's hydroxides and hydrogens involved depending on if the water is gaining or losing electrons, if it's being oxidized or reduced, because it is doing both. Some of the water molecules are being oxidized, some are being reduced. And describe a way to confirm that what's happening. Well, if we have these base particles at my cathode and the acid particles at my anode, what we can do is test pH or have an indicator in this beaker to see at which electrode we have a high pH or a low pH or phenolphthalein changing colors. That'll tell us whether we have hydroxide or hydrogen present and whether that's the anode or the cathode. Electrolysis of solutions become a little bit harder. When you put an electric current through, we always say that the easiest reactions happen first. Okay, that's point number 1. The easiest reactions will happen first, but then also, continuing the theme, your reactants have to be reactants. So if I have a solution of sodium bromide, I have water, sodium positive ions, and bromine minus ions. Those 3 things need to be reactants because those are the only 3 things available to put a current through. When we examine our reduction reactions, we find bromide and water are products over in the first 2 equations, and the water and the sodium are actually reactants in the second 2. So these 2 reactions we would have to reverse. These 2 we're going to leave alone. Okay, now I haven't decided how I'm going to multiply them, what my balanced equation is going to be, but I just need to reverse and compare. These are my 4 options. Since I have to reverse 2 of them, these are the 2 then that are going to compete with one another. So my bromide and my water in this top reaction, those are competing for electrons and energy. And when I give off electrons, because if I reverse these, they're both oxidation. They're competing for the oxidation half to lose electrons. If I reverse these voltages, I will have a negative 1.09 for my bromine and a negative 1.23 for my water. Out of those 2, once they're reversed, and I have to reverse those 2, 1.09 is easier. That tells me that this water reaction is not going to happen. I'm only going to get the bromine reaction. That's my anode half. The second 2, we're also going to make a comparison, but we don't have to reverse anything. I can just say negative 0.83 and negative 0.27. The negative 0.83 is easier, so that tells me my sodium reaction is not going to happen. That's my competition. I have a competition for the anode and a competition for the cathode. So once I set those straight and I reverse my reaction, I get 2 bromides. I reverse the bromide reaction, turns into bromine diatomic plus 2 electrons with a voltage of negative 1.09 volts. And then I leave my water alone, 2 H2Os plus 2 electrons. My 2 electrons happen to match, that's good. Make H2 plus 2 OHs. And the voltage there is negative 0.83. So I can add those voltages together to get my electrolytic cell potential, the current that I need to put through to make this happen. But most importantly is identified which of the two balanced equations will happen, and I can start discussing like what we would see, which one's the anode and the cathode, and we can start answering questions about it. So in order to figure that out, I had to find my reactants and make sure they actually were reactants, and then figure out for the anode competition which one is easier, and for the cathode competition which one of those is easier too. Okay, so here's another one with a competition. If we have a solution of iron 3 chloride, solution of iron 3 chloride. I have water in my solution. I have iron 3 ions and Cl minus ions. So I have to make those reactants because that's what I have available. So I start finding my chemicals. And now we start to see some trends here. The first two I have to reverse. This will be my anode competition. One of those will happen. And then here I've got 3 choices for my cathode competition. Okay, which one will happen and why? So the lowest energy things happen first. When I reverse my 2 anode reactions, we will find that the negative 1.23 is actually going to be easier. So this half reaction will occur because I have to make those negative. So negative 1.23 is easier than negative 1.36. And then of my 3 cathode reactions, the positive one is actually already a good value. This is the one that's going to happen. So my other reactions will not happen, and we can strike those out. The chloride will not be oxidized or reduced. Iron 3 is not going to turn into solid iron because it's easier to turn into iron 2. So that's a more favorable process. And we have our 2 half reactions. We will reverse the water, turning into oxygen and hydrogen ions. That'll be at my anode. And we can keep the iron one. We would have to match the electrons, add the balanced equation together, and add up the new voltages. If we can use the reduction potentials to figure out which favorable reaction will happen first, we can also use it to say which favorable reaction will happen first if I put a current in. So of all the negative ones that won't happen on their own, which one would happen first? We can use that idea to separate components of a mixture. So here we've got tin 2 turning into tin, so 2 electrons. And that voltage to reduce the tin is going to be negative 0.14 volts. To go from zinc 2 to zinc solid, that would be negative 0.76 volts. So we just look these up. And then to go from copper 2 to copper solid, taking me a minute to find that one. There it is. Positive 0.3 volts. So this one's very favorable. So if we had an electrolytic cell, assuming there's a second half that's being oxidized with these 3, that might still make it an electrolytic cell, we can rank them and say if all three of these chemicals are in a solution together and you put electricity in, the first thing that's going to happen is you're going to recover copper. All of the copper will react before any of the other chemicals. So once the copper reacts, then you'll be left with a solution of tin and zinc. Second, all the tin would react. So you get the copper, you can recover it out, and then you only have tin and zinc left. Once all the tin is gone, you will be left with a zinc aqueous solution. And if you keep putting in a voltage, you can get that third. Now, this is also a way to control like what you want, because the tin reaction, if all three of these chemicals are in a solution, we know that the copper is going to happen first. As long as I have a voltage between that 0.34 and that 0.14, depending on what the anode half is, as long as I keep my voltage between those and I don't let the voltage go high enough for this tin reaction to happen, I can only get copper. So I can control the voltage that I have enough voltage for copper to reduce, but not enough for tin. That way there's no risk of getting tin out. I can just recover all my copper. And then when I'm left with my tin and my zinc, I put a voltage in that's somewhere between this threshold of 0.14 and 0.76, and I can control the voltage so that this tin reaction happens, but not the zinc. Even once all the tin is gone, there wouldn't be enough electricity, enough of a current, or a voltage rather, to force that zinc reaction to happen. So that allows you to control which reactions happen by how much voltage you put in. If you don't want a reaction to happen, don't put in that much voltage. And now we get to the stoichiometry side of electrolysis, where we say, okay, we put a current through, how much metal can we recover, or how much of a certain chemical can we recover? And we need to know that our amps give us a conversion of coulombs per second, and we also have Faraday's constant for coulombs per mole of electrons. So the question reads, if 16.2 minutes, how many grams? So we've got our starting point and ending point, but we can start or stop anywhere along this path. So 16.2 minutes. And we know that for every minute is 16 seconds, and we need to do that to get into amps. So 3 amps gives me 3 coulombs per second. And we know that Faraday's constant, 96,486 coulombs for 1 mole of electrons. That is mole of electrons, not just moles. And then because we know this is copper 2 going to solid copper, there are 2 moles of electrons for every 1 mole of copper. So that's an important, we have our half reaction there that we can use to say copper 2 plus 2 electrons. That's our just stoichiometry with a half reaction goes to copper. So we're saying this is a 2 to 1 ratio. And then every mole of copper, normal stoichiometry to get into grams, 63.54 grams. This gives us 0.96. Let's do that first. Grams of copper. So this is a way to recover copper by putting a current through a solution. So very, very useful in industrial and chemical engineering. So this gives us, obviously we've got times, we can go the whole way through. Sometimes we just start with seconds, certain number of coulombs or amps. Sometimes, remember, we said in the slides, sometimes you'll see the word if you have like 1 or 2 Faradays. A Faraday is sometimes called a mole of electrons because of Faraday's constant. And then we can just convert to half reactions and grams, or we could go backwards. If we know we needed 0.96 grams, we could say, hey, it's 3 amps. How long does it take? 16 minutes. We can go backwards through that process as well. Here we have a similar electrolysis problem, but now it's a limiting reactant problem. Well, it's a stoichiometry problem anyways. This one's not actually limiting reactants. But we're talking about gases, so we can do gas stoichiometry as well. So let's do the same setup. If we had 12 minutes, 1 minute, 60 seconds, and 4 coulombs per second, so that's 4 amps. $96,486 coulombs for 1 mole of electrons. Sometimes this comes up on the AP test in the multiple choice section, and in order to do that, we would just round this Faraday's constant to 100,000, because again, we're just trying to get one significant figure. So the half reaction here, in order to get the number of moles in the half reaction, we want to go to the balanced equation. So we kind of pause here for a minute, and we know that we're going to decompose the water, and we're going to produce hydrogen gas and oxygen gas. And we would have to break these up and figure out how many electrons are being transferred here. We could do either the hydrogen or the oxygen as long as the stoichiometry is consistent. Okay, and we have to keep track of individual atoms. So going with our oxidation states, we know that the hydrogen has a +1 state and the oxygen is a -2, and then these are both zeros. That's important because it tells us there are 4 electrons being transferred. Hydrogen is going from 1 to 0, but there are 4 hydrogens. Oxygen is going from -2 to 0, but there are 2 oxygens. So both of those give us 4 electrons. We can look at either half to figure it out and say there are 4 moles of electrons total, and we could either compare that to the hydrogen or the oxygen. So 4 moles of electrons will give us 2 moles of hydrogen. I'll do the hydrogen one. And we could obviously simplify that if we knew that just the hydrogen half reaction was 2 electrons, but since we have the balanced equation, we know there's 4 electrons with 2 moles of hydrogen. And now that we're in moles, instead of going to grams, we're just going to say there are, every 1 mole of gas for hydrogen gives me 22.4 liters of hydrogen gas. And we can only do that under ideal conditions. So that gives me 0.334 liters of hydrogen. Now we could do that same thing with oxygen. Obviously it cuts off halfway through and just takes it a little different way. Or we could just look at the stoichiometry. We know that for every 1 liter of, every 2 liters of hydrogen is going to give me 1 liter or 1 volume of oxygen. This is a 1:2 ratio. We can do stoichiometry with gas volumes, which is a nice little spot to end the year. Just kind of reviewing a little bit of gas stoichiometry that we did so long ago. And that would give us half the volume of the oxygen and the hydrogen. So 0.334 hydrogen, 0.167 liters oxygen.